Okay, so previously we were looking at the magnetic field of a wire through which current I is flowing, right? They say this wire is carrying current I, okay? Its magnetic field is H, which is encircling, right? Current I is flowing, magnetic field is encircling. This magnetic field is proportional to current I divided by a constant 2 pi divided by rho. And the rho is the distance, this one, rho, from the center of the conductor, to the magnetic line of force. Probably there's another magnetic line of force in which you are interested, this blue one, right? So then the magnetic field intensity of the blue lines of force will be equals to I divided by 2 pi rho. Okay, rho is that distance. Okay, and this magnetic field is in the phi direction, so we have this phi direction. We also know the electric field of a line charge, a static line charge, which is this much. The magnetic field of a same line, but if the charge is not static, if the charge is moving, then it has the magnetic field, which is this much. So we know these two from our previous lectures. We also went through the Ampere's law, right? Ampere's law sums up this current I. So if there's a magnetic field intensity H around the wire, right? The magnetic, if you somehow can detect the magnetic field intensity, you can calculate the current I. Okay, so current I is through the wire is the magnetic field dot dl, closed loop, right? So that's the magnetic field around the wire. Okay, uh, so the magnetic field, you can calculate the magnetic field intensity using the Ampere's law. Ampere's law is H dot dl a closed loop equals to I enclosed. Okay, so H dot dl, H is the magnetic field intensity, suppose this one. Okay, say this is the magnetic field intensity of a wire through which current I is flowing. So H is in the phi direction, integral dl. This dl, if I take this small differential length dl, okay, this small one of the magnetic field lines of force, then this integral is I enclosed. So H of I, what is this entire closed loop? What is this entire closed loop? Length of this circle is circumference of the circle, right? Which equals to 2 pi r, which in this case is 2 pi rho. So r is the radius, so the length of the circumference is 2 pi rho. Okay, so this integral, the closed loop integral, will really go from 0 to 2 pi. Okay, equals to I enclosed. Okay, I enclosed. So if you evaluate this in entire equation, it will be h of I dot, this entire thing is the circumference 2 pi rho. So it's 2 pi rho, which equals to I enclosed. Okay, this circumference is I enclosed. बात ही समझ आ रही है? Any question here?
No, sir.
No? Okay. So from this equation, really you are going to get this equation. So that's the amount of magnetic field intensity around the wire. Okay. What if you are interested in the magnetic field intensity? What if you are interested if current I is flowing through the wire? There's a magnetic field intensity inside the wire. Okay, H inside. You remember, the electric field was zero inside the conductor. The magnetic field is this much. There's a magnetic field intensity outside the wire. This is outside the wire, right? So you can really it's this same equation, I equals to sorry H equals to I divided by 2 pi rho in the direction of phi, but for this rho is greater than the radius of the wire. The radius of the wire is A. And for the magnetic field intensity here, uh, it's really an equation which we need to calculate. We need shortly we have to calculate this equation. Okay, so inside the wire we need to calculate. Outside the wire we have this particular magnetic field intensity. Okay, so this is the outside the wire. Outside the wire, the magnetic field intensity is this much. Go through this descriptions. And you really use the Ampere's law to calculate magnetic field intensities. Inside the wire, the magnetic field intensity is H dot dl equals to I inside. Okay, I inside. So H dot dl, Ampere's law, closed loop integral equals to I inside. If you are calculating the H magnetic field intensity inside the wire. Okay, so if you are calculating it here, okay, magnetic field intensity here, this one, the H inside. So you will calculate the current which is here, I inside, I inside. So really this current, the current in this region you are not considering. The current in this region, because this is the entire cross section, you can see this is the wire. If current carrying wire cross section. Okay, so if you are interested in calculating H magnetic field intensity here, you are really not considering the current which is flowing through this cross section of the wire. You are interested in the current which is in this region. Okay, so of course that will be a reduced current. Okay, that will be a reduced current because look, the current will stay the same. The current will stay the same, but the current density will be different. Okay, current density, because current density J, current density is equal to I divided by area, cross sectional area. Okay, so I divided by area. Okay, so I inside this one, if I say I inside equals to J of the wire, the current density of the wire. Okay, remember it's the density, it has to stay the same value. Okay, the current density throughout the cross section of the wire will stay the same. This is the cross section of the wire. Okay, so no matter you consider the blue cross section of the wire, the current density here will be the same. Okay, just let me make a little correction here. Probably a few minutes back I said the current will stay the same throughout the cross section. It's the current density which will be constant throughout the cross section. So the current density throughout this cross section, J, the black current density throughout the entire cross section of the wire is same as the J of the blue region. Of course, it's the density. So in the blue region, less current, but the area is also less. So the constant, so J will stay the constant. J will stay constant. Okay. So blue I in the blue region, in the blue cross section, since the area is less than I of the entire cross section, which is the black cross section. I is less, but J is the same. Are you getting this thing? Is this okay? So, so since J is constant, okay. So, so what is the J A if I say, let me make a little adjustment here. So if I say J black J over total cross section equals to blue J blue cross section, okay, blue cross section. Or if I say, if I call this blue cross section as the J inside, let I call this as the J inside. J black is the total cross section, J inside is the blue cross section. Okay. So what is J black? J black is how much current I, okay, the total current I in the wire, total current I in the wire. I is the total current in the wire, okay, divided by what is its area of the total wire area, the black area, the entire cross section is 2 pi, sorry, not 2 pi, is pi rho square, because pi rho square, rho is the radius of the wire, okay. Sorry, rho is let me check yeah, rho is rho is only to this point. A is the radius of the wire, okay. A is the radius of, so I'll put a here, a square here, equals to I inside, because J inside, I'm talking about the J inside, so it's I inside divided by area of the inside this region, this blue area, okay. So pi rho square, okay, pi rho square, okay. So what is from here? I inside, I inside is how much? बताएं. I total,
Our area.
yeah, I total divided by pi a square dot कौन सा, ये पाई रो स्क्वायर इधर आ जाएगा ना ऊपर, ऐसा ही है, ठीक है. बात की समझ आ रही है? Is this okay? We just use the ratio concept here, nothing else. A very simple, very basic ratio concept. So this is the I inside. So now if I'm interested in calculating H inside, this magnetic lines of force H inside, okay. So it will be, H inside will be equals to how much? I बताए, जल्दी से बताए. It will be I inside divided by
Yeah.
what? Divided by what? Divided by what? हमारे पास इक्वेशन है ना, ये देखे ना, ये इक्वेशन है ना हमारे पास H की, ठीक है. ठीक है, अगर इससे मैं निकालू H इनसाइड को मैं कैलकुलेट करना चाहूँ, ठीक है, इस इक्वेशन से. ओके ओके, वेट, let me copy this equation here and I'll paste it here, okay. Okay. So if I'm interested in calculating H inside, so this I will be I inside, ऐसा ही है.
inside.
हाँ, अब I inside की जो वैल्यू है वो पुट करें इस इक्वेशन में. ये जो I inside की जो वैल्यू है, plug it here. Okay, if you do that, H inside कितना आएगा? I inside की क्या वैल्यू है? I total, which is the black thing. I total, let me remove this line. I total divided by I total divided by I total pi rho square divided by pi a square divided by 2 pi rho. This pi rho square was the blue thing from here. Okay, divided by 2 pi rho. Okay, divided by 2 pi rho. बात की समझ आ रही है? Is this okay? So see, this square will go away with this row. Okay, this pi will go away with this pi. So you will left with, and let I remove this total from here because I understand it's the total current. I divided by 2. Here we have rho, and this will come into denominator 2 pi a square, and it will have the same direction phi. Okay, so this is the amount of magnetic field intensity inside the wire. समझ आ रही है ना बात की? If I consider, so H inside equals to I rho divided by 2 pi rho, so not 2 pi rho, 2 pi a square in the direction of phi. Okay, H on the surface is how much? सरफेस की कंडीशन क्या होगी? रो इज इक्वल टू ए. ये सरफेस की कंडीशन होगी ना, रो इक्वल्स टू ए. सो आई रो डिवाइडेड बाय 2 पाई ए स्क्वायर इन द डायरेक्शन ऑफ फाई. रो और ए एक ही चीज है, रो और ए एक ही चीज है. सो रिप्लेस रो विद ए. A will go away with A, or replace A with rho. It's really your choice, whichever you like. This will go away with this one. So ये कितना रह जाएगा? I divided by 2 pi rho, which is equal to H outside, which equals to H outside. बात की समझ आ रही है? तो ये हमारे पास मैग्नेटिक फील्ड इंटेंसिटीज है. ठीक है? Is this okay? Okay. So now, I have so when the current I is flowing through the conductor, there's a magnetic field intensity inside, there's a magnetic field intensity outside. Magnetic field intensity inside is this much, the outside is this much. It's that simple. Okay. What if instead one wire I have a coaxial cable, and current I flows through this. If I have a coaxial cable, okay, so I know that there will be a magnetic field intensity inside the wire, there will be a magnetic field intensity outside the wire, there will be a magnetic field intensity in the outer wire. Okay, so let me make it like this. There's a magnetic field intensity inside the wire when current I flows through the wire. There is a magnetic field intensity outside the wire This magnetic field intensity inside the wire is this equation. The magnetic field intensity outside the wire is this equation. And there will be another magnetic field intensity which is outside the outer wire. Here, there will be another magnetic field intensity outside the outer wire, which is this one, right? Sorry. The third magnetic field intensity here in this region. Okay, this is E inside outer wire of the coaxial cable, and we need to calculate this. Okay, because the other two are known and the third we need to calculate. Okay, so again, if I'm interested in calculating this intensity in the third wire, I will really use this Ampere's law again. Go through this little mathematics, and you will find that the third intensity, this intensity, which is the intensity inside outer wire, is this much. Okay, so now we have the magnetic field intensity for all the three regions. Magnetic field intensity inside inner wire is this equation. The magnetic field intensity inside the outer wire is this equation. Okay, and the magnetic field intensity inside the outer wire is this equation. Okay, and the magnetic field intensity here outside the outer wire is 0. Okay, so the magnetic field intensity H outside outer wire is 0. Just like with the electric field outside outer wire of coaxial cable was also 0. So we have now this complete diagram. Okay, here you can interpret few results. Suppose if I draw this one, this is, if I draw this one as the axis of the coaxial cable, and this one as we move from here, as we move from here to here, then here, then here, right? So say this is the row axis. Okay, this is the row axis, and this is, suppose the vertical axis is the strength of magnetic field intensity. Now look here, look here, when I move from here to here, from the center of the inner wire to the surface of the inner wire, rho is increasing. The other things are constants. Rho is increasing. So magnetic field intensity in this region is linearly increasing. When rho is 0, the magnetic field intensity is 0. So right at the center, magnetic field intensity is 0. But when I'm just trying to draw a graph here, right? So when in this region, this is point A, radius of inner wire. This is outer radius of outer wire. This one is the inner radius of outer wire. So see, you can make these calibration sort of things. Okay, but see, magnetic field intensity will linearly increase with rho as you move to A. And then if you further increase rho, if you go beyond this region, if you go beyond this region, magnetic field intensity is reducing here. And again, linearly, inversely reducing, right? So it's reducing here. Okay, it's reducing again. And when you in the outer wire, and if you it's reducing again, but with a square difference function. Okay, so it's again in this region to this point, to this point, it's reducing, but here it's reducing further. It's reducing quickly with a square function. Okay, the square sort of function introduces, and here it stays zero. So this is a kind of graph you can produce with the magnetic field intensity. Okay. Okay. Any question here? So if you take the coaxial cable, you can calculate the magnetic field intensity at different parts of the coaxial cable. Now let's define the inductance. Uh, we know the definition of inductance. L is equal to flux linked to current I. We will explain this flux in our next class in detail. You already know about it. You already know about it. So you know that when a time varying current I is flowing through a circuit, it links the secondary wire through flux. Okay, the secondary wire through a flux, and there's an electromagnetic induction phenomena. So that we already know, and we'll talk a lot in this flux in our next class. But from basic, you know the definition of the inductance, that is phi divided by the current I through the wire. This basic definition is already known to you. And the energy, the magnetic energy is half inductance current I square. So if there's current I in the wire, this is magnetic energy. And inductance is, from this equation, inductance is 2 magnetic energy divided by I square. And the magnetic energy, this is the magnetic energy, or the energy stored in magnetic field, magnetic energy, or the energy stored in the magnetic field is half magnetic flux density, and this is magnetic field intensity. So these are the few equations which are already known to you. Energy is half volumetric integral, volume integral of B dot H. B dot H. This is B dot H. A little problem with the fonts. You see this dotted kind of square, but it's actually the dot thing. Okay, B dot H. Okay, and remember B is equal to mu naught mu r h. Again, we'll make some discussion on this mu r thing in next class. Okay, but for a while, just use it as a number here. Okay. Okay, so this equation is known to you, the inductance, right? Now look here. If I know the magnetic field intensity inside inner wire, I can calculate inductance of inner wire. Okay. Uh, Similarly, if I know the magnetic field intensity outside inner wire, if I take the coaxial cable, remember, magnetic field intensity, I know outside the inner wire. I can really calculate the inductance of outside inner wire. Okay. If I know the magnetic field intensity inside outer wire, I can really calculate the inductance inside outer wire. Okay, let me bring a picture of this here. Okay, if I consider this thing. Okay, so this thing is here. This thing is here. Okay, and this one is here. Okay, I can do that. Okay, just by implementing this equation. Okay, and the magnetic field intensity outside outer wire is 0. This implies that inductance outside outer wire is 0. Okay. Now, how to calculate this thing? L, L, Acha, right. Can I can I rename this as the inductance of the gap of the inner wire gap between inner wire and outer wire? Yeah. So I can calculate the inductance of inner wire. So what should be that? It should be integral B dot H. B dot H divided by, it's a volume integral, divided by current I square. Now I can do one more thing here. B is mu naught mu R. B is mu naught mu R H dot H. Okay, when the two vectors are dotted together, the dot product of two vectors will only give you the magnitude. Remember, so I can really calculate this thing now. See, mu naught mu r, they are the constants. They are outside the integral now. H, the two vectors, you end up on the magnitude square. If you dot the two vectors, you get the magnitude square divided by, so volume integral divided by I square dV. So what is this H? H is L inner wire. So H is magnetic field intensity inside inner wire. उसका मैग्नीट्यूड स्क्वायर हो गया. ठीक है, या आप क्या करें, डॉट करें H को उसी नंबर के साथ, उसी वैल्यू के साथ इनसाइड inner wire. Okay, it's really your choice, but we know that if you take the dot product, you end up on the magnitude square. So now if you plug the value of this thing, if you plug this value here and here, you will calculate this one. Okay, बात की समझ आ रही है? Okay, so from here I will calculate L inside. From here I will calculate L gap, and from here I'll calculate L inside outer conductor, and here L is 0, outside the outer conductor, right? So what should be the total inductance? Total inductance of coaxial cable equals to L total equals to L inside plus L gap plus L inside outer, no, L outside the outside outer conducting. Okay, so that this way I can calculate the entire inductance of the coaxial cable. तो वो थोड़ी सी मैथमेटिक्स है, I leave that mathematics to you. See, the inductance of the inner wire is calculated here. Okay, plug the values here and you get this thing. This is the inductance of the inner wire, this one. Okay, go through this mathematics and you will be able to calculate the inductance of the gap here, this gap. Okay, very straightforward mathematics. I leave this mathematics to you. Okay, and then you can really calculate the inductance of the outer wire. Outer wire. Okay, total inductance कितनी होगी? Total inductance कितनी होगी? Total inductance will be inner plus gap plus outer, and it's this much. Okay, this is total inductance. You remember coaxial cable total capacitance was this much. This was the total capacitance of the coaxial cable, and this one is the total inductance of the coaxial cable. Okay, if you multiply these two together, inductance multiplied with the capacitance. If you multiply this total inductance of the coaxial cable with this total capacitance, few things will go away. 2 pi go away, this 2 pi. You left with mu r, mu naught, epsilon r, epsilon naught. This entire thing is mu. This entire thing is epsilon. Okay. So this is the total inductance. Now look, this very interesting equation. The product of the total inductance and capacitance of the coaxial cable is very interesting equation. If I say the velocity, if I say the velocity, the phase velocity of electromagnetic wave inside a coaxial cable, because there is electric field, there is magnetic field. Okay, ये देखे ना, ये अगर कोएक्सियल केबल है तो हमारे पास क्या है? अगर ये कोएक्सियल केबल है, हमारे पास यहाँ पे क्या है? इलेक्ट्रिक फील्ड है, और यहाँ पे क्या है? मैग्नेटिक फील्ड है. यहाँ पे भी मैग्नेटिक फील्ड है, यहाँ पे भी मैग्नेटिक फील्ड है. ओके, हमारे पास तीनों फील्ड, दोनों फील्ड्स है. फेज वेलोसिटी अगर मैं सम अप करूं, दो आई एम गोइंग इन लिटिल रिवर्स वे, बट सॉल्यूशन के बाद आपको पता चल जाए कि व्हाई दिस प्रोडक्ट इज सो इंपॉर्टेंट, द कैपेसिटेंस एंड इंडक्टेंस प्रोडक्ट. इफ आई से द फेज वेलोसिटी ऑफ इलेक्ट्रोमैग्नेटिक वेव, say this is the, suppose this is the inner wire of the coaxial cable, this is the outer wire of the coaxial cable. देखिए दो तारे हैं ना coaxial cable की, Suppose the inner wire is this one and the outer wire is this one. Just for example, when you apply voltage to it, the TV signal to it of many frequencies, when you apply the TV signals to it, the voltage to it, current I will be through it, and that will constitute electric field and the magnetic field. Electric field and the magnetic field. That electromagnetic wave is going to travel through this gap. Okay, so let's see what happens to that electromagnetic wave. It's mu r 1/√ mu r mu naught epsilon not epsilon r, right? Epsilon, I can call this as 1/phase velocity square. Okay, so from this equation, I have these few results. So phase velocity is 1/mu r, sorry, it's mu naught epsilon naught √ dot mu r epsilon r, which is 1/√ what is mu naught? 4pi into 10 to the power -7. What is epsilon naught? 8.856 into 10 to the power -11. ऐसा ही है ना? Dot 1/mu r epsilon r √ okay. If you try to calculate, if you try to solve this through your calculator, this number is nearly 3 into 10 to the power 8. This entire number, 1 divided by 4 pi into 10 to the power -7 into 8.856 into 10 to the power -11. You take a product of this and then take square root and then take a reciprocal of it. You'll get this number, nearly this number, 3 into 10 to the power 8 meter per second, which is speed of light, divided by mu r epsilon r √. So that is the phase velocity. So it's very interesting. When you multiply the capacitance of the coaxial cable with the inductance of the coaxial cable, you will really get the phase velocity of the electric and magnetic fields inside the coaxial cable. If you apply the time varying signals to it of very high frequencies and many frequencies, and very high frequencies. Okay, so there are many frequencies in this signal. Okay, in the form of voltages. Remember, they all are in the form of voltages. Okay, there's a voltage signal to the coaxial cable, to the inner conductor, outer conductor. And here you connect probably is your TV. Okay, बात की समझ आ रही है? So this is 3 into 10 to the power 8 meter per second divided by the refractive index of the coaxial cable. So phase velocity in coaxial cable is the speed of light divided by refractive index of the coaxial cable, and refractive index of the coaxial cable in refractive is mu r of the coaxial cable divided by epsilon r of the multiplied by epsilon r of the coaxial cable. So there's a dielectric material here which has certain epsilon r and which has certain mu r. The coaxial cable. बात की समझ आ रही है?
Yes, sir.
अच्छा, अब देखिए, for example, if I take an example here, suppose we have a coaxial cable whose epsilon r is suppose 12, okay, and mu r is 1. So what should be the velocity of electromagnetic wave through it? Vp will be 3 into 10 to the power 8 divided by 12 multiplied by 1. So Vp will be speed of light divided by under root 12. So reduced speed. ठीक है, स्पीड थोड़ी सी रिड्यूस हो जाएगी. सपोज आप एक लाइव टेलीकास्ट टीवी पे देख रहे हो. इन टू केसेस द टेलीकास्ट इज कमिंग थ्रू एयर, यू आर रिसीविंग इट थ्रू एंटीना, एयर से आ रही है. दूसरी केस में आपके पास दूसरा टीवी है, वही लाइव टेलीकास्ट आप कोएक्सियल केबल से, केबल टीवी से देख रहे हो. तो इलेक्ट्रोमैग्नेटिक वेव जो आपको टेलीविजन की ब्रॉडकास्ट पहुंचा रही है, एंटीना के केस में आपको कुछ स्प्लिट ऑफ अ सेकंड पहले रिसीव होती है बनिस्बत कोएक्सियल केबल के, क्योंकि कोएक्सियल केबल में इलेक्ट्रोमैग्नेटिक वेव की स्पीड क्या हो रही है, रिड्यूस हो रही है. तो कोएक्सियल केबल में वो थोड़ी देर बाद आपको होती है, लाइक अ स्प्लिट ऑफ अ सेकंड, लाइक लाइक टेंथ ऑफ अ सेकंड डिले के साथ या हाफ अ सेकंड डिले के साथ वो आपको पहुंच रही है, बिकॉज ऑफ द mu r and epsilon r of the coaxial cable that reduces the electromagnetic wave speed. Okay, so that, so it is very interesting that you consider the capacitance of the coaxial cable and you consider the inductance of the coaxial cable, and when you multiply the two together, it is going to give you the velocity of the electromagnetic wave through that coaxial cable. A little interesting situation. Okay, so I hope it's enough for the day. आज थोड़ा सा आप लोगों का काम ये है कि जो नेक्स्ट हमारा हम एक टूल यूज करेंगे अगले लेक्चर में, वो है कर्ल ऑपरेटर. तो उस कर्ल ऑपरेटर को थोड़ा सा आप देख लें, बिकॉज यू ऑलरेडी नो अबाउट इट. ठीक है, तो कर्ल ऑपरेटर ये 2-3 स्लाइड्स आज आपने देखनी है. सो विल कंटिन्यू विद द डिफरेंशियल फॉर्म ऑफ एम्पेयर्स लॉ फ्रॉम द नेक्स्ट क्लास. Okay. Any question here?